Today we are going to see an experiment on beam with combined loading. So the objective of the experiment is to determine the principal stress and principal plane of a given hollow section subjected to both bending and torsion. That is both combined loading. We are going to apply both bending and torsion. So here I have shown the schematic of the beam setup. So if I see, you can understand, we are going to use a cantilever beam. So one end is fixed and one end is free. And the cross section of the beam is hollow section. So now, as I mentioned earlier, to apply torsion load, we need to have an arm. So if you see, maybe in the next session, you can see the physical view of that beam setup. So here we have kept the arm like this. So by using this arm, so this is the side view of the arm. So by using this arm, we are going to apply the load like this. So this is the arm. So here I am going to apply the vertical load. So by doing so, the beam will be subjected to both bending and torsion. That means bending will lead to deflection and torsion will lead to twist. So this is what we are going to do. So now again I am conveying the objective of the experiment. We are going to compute the principal stress and principal plane of the given beam subjected to both bending and torsion. So now we will see the geometrical parameters of this beam. So the beam has a length of 550 mm. So now we have taken 3 different points A, B, C. So in order to get that deflection or strain, so just I am showing the distance between the section A and free end. It is L1. So L1 is given as 490 mm. Again, the distance between the section B and free end is L2. It is defined as 370 mm. And the distance between the section C and free end is L3, which is given as 250 mm. So now we have defined all the 3 sections A, B, C. So again, in order to get the strain, we have mounted strain gauge on the top of that beam and on the bottom of the beam. So by doing so, we will get the half-bridge circuit. This about the strain gauge details we will discuss in the later sessions. So as of now, you can keep in mind that we are going to use 2 strain gauges to get the strain at the section A. So by using 2 strain gauges, we will be using half-bridge circuit. So again at section B, the strain gauge has been mounted at 45 degree. The purpose of mounting at 45 degree is to get the shear strain. Again for section B, we use single strain gauge that leads to quarter bridge circuit. Again coming to C, again here to compute the normal strain due to bending, we use two strain gauges at top and bottom of section C. Again this leads to half bridge circuit. So this is the location of the strain gauges, and I have mentioned the geometrical parameters of this given hollow beam section. So again, if you see here, I have already mentioned that we use a hollow circular cross section. So the outside diameter of the beam is 50 mm, and inside diameter is 44 mm. It has thickness of around 3 mm. So this is what the schematic of the given beam setup. Now we will see the tabulation and how to get the readings from the given beam setup, and then we will see the theoretical formulae to compute the principal stress and the principal angle of the given beam subjected to combined loading. So now we are going to see how to get the readings from the given beam setup. So here we have the schematic of the beam setup. So already I mentioned the cantilever beam. We have taken 3 points A, B and C, and each point we have strain gauges to get the strain data. So we are going to apply the load at the free end, that is called W. Okay. So for first reading, I apply a load of 2 kg. For the 2 kg, I can get a strain of 20 microstrain. Here micro stands for 10⁻⁻⁶. So this this reading we can get from the given strain gauge indicator. So when I apply the load, the beam will try to bend like this. So when it bends, there will be strain will occur. The strain can be determined from the strain gauges, that is, which is noted on the section A. So we have two strain gauges. So from this strain gauges, I am getting a strain of 20 microstrain, that is 20 into 10 to the minus 6 strain. Now again, we also can get the strain at section B. As I mentioned earlier, this is the section we are going to measure the shear strain. That is why this strain gauge is mounted at the angle of 45 degree. So we get around a strain of 3 microstrain. So now go to section C. So section C, again we have two strain gauges. So we get a strain of 10 microstrain, which we are getting due to the applied load of 2 kg. So now we have noted the corresponding three strains, that is strain at A, strain at B and strain at C for the given load of 2 kg. Now from this we need to compute the normal stress and the shear stress. How to do it? So we all know that the load which we apply is within the elastic limit. So and also the material which we use is isotropic material and homogeneous material. So we can apply the Hooke's law. So what Hooke's law says? It says that stress is proportional to strain. So this is the formula which we get from Hooke's law. So we want the stress. So already we know the strain at section A. So we know the metal property. The Young's modulus of the given beam is 70 gigapascal. It is made up of aluminum. So we know the Young's modulus of the aluminum is 70 gigapascal. So 70 gigapascal into the strain will give the strength or the normal stress at section A. So here, if you notice here, I am multiplying by 2. So why I am multiplying by 2? Because we use two strain gauges at section A. So this leads to half bridge circuit. So generally we use Wheatstone bridge circuit to get the strain data. So as we are using two strain gauges, we need to use half bridge circuit. If we use four strain gauges, then it is called full bridge circuit. If we use one strain gauge, then it is called quarter bridge circuit. So that is why as we are using half bridge circuit, we need to multiply by 2 here. So the Young's modulus into the strain into 2 will give the normal stress or the bending stress at section A. So now I got my stress. Okay. So I got some value here. Now what is next? We need to compute the shear stress, that is tau. So as I mentioned earlier, at section B the strain gauge has been oriented at 45 degree. This will give shear strain. So you can write epsilon B or gamma. So this is strain which we get from section B. So we got 3 as the 3 microstrain at section B. So again we use the same formula. You can write sigma B or tau. So this is the stress at section B. Again we apply the Hooke's law. E is the Young's modulus of the given material. Epsilon B is the strain at section B into 1. Why I put 1 here? Because we use only one strain gauge at the section. So we need to multiply by 1. So from this we get our shear strain. So shear stress. We get shear stress. So now for the given beam subjected to combined loading, we have got the bending stress and shear stress. Now what is next? So our objective is to compute the principal stresses and angle of principal plane for the given hollow section beam subjected to combined loading. So now I have got the Cartesian components of the stress components, that is normal stress and shear stress. Now from these Cartesian components, how are we going to compute the principal stress? So again we need to go back to the theory, the solid mechanics theory. So already we have seen in that theory course. So this is sigma 1, sigma 2 is the principal stresses. So what is principal stress? So just quickly I'll give you a recall about the principal stress. So principal stress is the stress acting on the plane where there is no shear stress. So we can have two principal stresses, one is maximum minimum for a given structure. So this is the formula. So sigma 1 sigma 2 is equal to sigma x plus sigma y by 2. So sigma x is nothing but the stress acting on x direction, sigma y is nothing but sigma stress acting on the y direction by 2 plus or minus. If I put plus, you get sigma 1, that is maximum principal stress. If you put minus, you get sigma 2, that is the mean principal stress. Or in other words, you can say sigma 1 stands for major principal stress and sigma 2 stands for minor principal stress. So again sigma x stress acting on x direction, sigma y stress acting on y direction by 2 the whole square plus tau x tau square square. So again here tau is nothing but the shear stress. So now here we don't have any stress acting on the y direction, so you can ignore this y as of now. So just plug in the sigma x or sigma a and the tau in this formula. So when you plug in and when you do the calculation, you get sigma 1 and you get sigma 2. So now we have computed the principal stresses of a beam subject to combined loading. So now we have one more objective to be discussed. It is what is the principal angle or the angle of principal plane. So this is the formula. Again, tan 2 pi is equal to 2 tau x y by sigma x minus sigma y. So tau is known to us. We can get from this column, and the sigma is we can get from this column. So we know both normal stress and shear stress. Again, sigma y is not there is not any vertical stress. There is no stress acting on y direction, so you can ignore it. So just to plug in the tau and sigma x, you will get the angle of principal plane. So now what we have done, we have taken a beam, a hollow section beam, and we applied a combined loading. Just now we have seen the beams set up. So we apply both bending and torsion. So for this combined loading, we wanted to compute the principal stresses and principal angle. So now we have got the principal stress and principal angle for the given loading of 2 kg. Now we can do it for the second set of loading. So now add the load from 2 to 4 kg. Now measure the strain at A, B and C. Note down the strains. Now use the Hooke's law formula. Get the bending stress and the shear stress. So once you get the Cartesian moments of stresses, apply this stresses in the principal stress equation. You get again the principal stresses. So this way you can compute the principal stresses and principal angle for different set of. Yeah, so far we have seen how to compute the principal stresses and principal angle experimentally. So now I am going to explain how to compute principal stresses and principal angle of the given beam subjected to combined loading theoretically. So now again for the first set of loading 2 kg, previously we got the strain from A, B, C, right? From the strain we used the Hooke's law to get the stress experimentally, correct? Now we are going to compute this stresses theoretically. So now to compute the bending stress or the normal stress of the given beam subjected to combined loading, I use theory of bending. So we all know the very popular fracture formula, that is M by I is equal to sigma by y is equal to E by R. So this is a very famous fracture formula. So from this formula we can compute the bending stress. So sigma is equal to M y by I. So what is M? M is nothing but the applied bending moment. And what is Y? The distance from the neutral axis. And what is I? It is the cross-sectional property, or we can say moment of inertia. So this moment of inertia depends upon the geometry of the cross-section. So now I am going to apply a load of 2 kg. But how are you going to convert the load into moment? So see here, this is a typical candidate beam. I am going to compute the stress at section A. So what is moment? The load into the the particular distance. So what should I do? So here M is nothing but W into L1 will give the moment. So when I apply a W at the free end, I get a moment of W into L1 at the section A. So now I got the moment. Now what is Y? I told this is from the neutral axis. So we all know that for a circular cross section, the neutral axis would be at the middle of that beam. So we know that the maximum stress would be occurring at the top or bottom of the beam. So I can write my Y as D by 2. So D is diameter, D naught by 2 would be the Y. So D naught by 2, the beam will experience the maximum stress. And what is I? Again I told it's the geometrical property. For a circular cross section, it is pi d power 4 by 64. But here we use a hollow circular cross section. So pi into outside diameter power 4 minus inside diameter power 4 divided by 64. So now we know all the values. We know the applied load, applied moment. We know the distance from the neutral axis, that is at the top is d naught by 2. We know the moment of inertia. Just plug in all the values, you get the stress. Just write the stress here. You get some 20 or some value, some 20 millimeter square. So now we have computed the bending stress or nominal stress of the given beam subjected to combined loading. Now what is next? We need to compute the shear stress. So to compute the shear stress, we go for theory of torsion. So this is the formula which we get from theory of torsion. Again, we all know the formula. T by J is equal to tau by R is equal to G theta by L. So this is the very famous torsion formula. So from this formula we can compute the shear stress. So what is shear stress? Tau equal to T into R by J. So what is T? T is the torque, the applied torque. So how we are getting the torque? In the beginning I told we are going to use here, we are using an arm, right? Like this we are going to use an arm, right? At the arm only we are applying that load. So now the torque would be nothing but the applied load into this arm, which is called the torque. So T is nothing but the W into the X. So X is nothing but the length of the arm. So by doing so, the beam will be subjected to torsion. So now we got the torque, applied torque. Now what is R? It is radius of the pipe. Again, it's radius. We know, right? D naught by 2, same. That is the radius of the pipe. And what is J? It is polar moment of inertia. Again, it's a geometrical property. So for a solid shaft, it is pi d power 4 by 32. As we are using a hollow section, it is pi into outside diameter power 4 minus inside diameter power 4 by 32. So now we know the applied torque, we know the diameter, we know the diameter of the given section. Also we know the polar moment of inertia. Just plug in all the values, you get the shear stress. So now I got the nominal stress or bending stress from theory of bending, and also I have got the shear stress for by using the theory of torsion. So now I have the nominal shear stress. Now take these two values and apply in the principal stress formula. So as I mentioned earlier, there is no stress acting on y direction. You can ignore this. So sigma x you can take from here. There is bending stress, and tau again is here. Just now we have computed from theory of torsion. Just apply here. So you will get the major principal stress and minor principal stress. So now we have to compute the angle of principal plane. This angle by again we use the same formula which we used for experimental readings. So tau is the shear stress, tau x is the shear stress, and sigma x is the nominal stress. So just apply the value, you will get the principal angle, the angle of principal plane. So by this way we can calculate the principal stresses and the principal plane of the given beam subjected to combined loading. So today we have learned to compute these stresses both experimentally and theoretically. Okay.
So this is a setup for combined loading. So for this beam, we have combined loading, which means we have direct bending and then torsion. So for this, we have a cantilever beam of length 554 mm, and then we have an extended arm. Directly, if you apply load here, it is going to cause pure bending. If you have an arm and then if you apply load at that point, it is going to cause bending plus torsion. So this is of 3 mm thickness, and to measure the required parameters, we have 3 strain gauges located at 3 different locations. So the first location is marked as A, and we have a strain gauge on the top surface. Then we have B location where the strain gauge is placed at 45 degree, and then we have the third location which is marked as C, and we have a strain gauge on the top surface. These are connected to a digital indicator where you can see a digital indicator with a display where you can measure the strains from the strain gauges. We have multiple switches here. One is to select the channel. So you have 3 channels which is connected to 3 ports here. So you can select from which channel you need to measure the strain. So this is going to be the channel selector, and then you can select which bridge you want to use, whether it is a quarter bridge, half bridge or full bridge, that you can select here. Then we have the refinement levels, whether you can refine it in coarse way or in a very fine way. So coarse way will be doing in terms of hundreds of thousands, and then fine it will be in very fine numerics. So you can set your desired value before starting the experiments, and then you can add the load in the hooker, and then you see what's the strain at the given points using the channel selector, and you can record the given strain values. First loading. Okay. Unloading. We'll start assembling. First the hook, weight hanger is done. Then switch on the experimental setup, and then set the dial indicator for 0 using the coarse and fine knobs. To dismantle, first remove the weight hanger from the hook. Okay. Then switch off the experimental setup.